Hello, everyone. Good afternoon. I think we going to start the webinar. Uh, I'm Nabil Mancheri. I'm the senior advisor at the EIT RawMaterials. This is the eighth event in our roundtable series, where EIT RawMaterials Strategic Impact Group Network on Rare Earths and the Horizon Project MAGELLAN jointly organized this series. And the MAGELLAN projects is looking at producing high efficient magnet from the recycled route, which is coordinated by the leading industry player Orano, and where we have a number of partners from across Europe, from representing industry and academics. And this one is all about LCA, life cycle assessment. There is a great traction on this topic, and there are also some mandates related to LCA from the European Commission. And we have seen we have about 350 registrations for this webinar, and we see why it's so important. And we have four speakers today, all leading expert on the LCA and have been in this field for some time. So the first one is Robert Pell, and he is the CEO and the managing director and founder of the Minviro, which is a leading LCA provider, has been in the industry for long, have done fantastic work. He did his PhD at the University of Exeter. We were kind of started our academic journey almost same together. So know Robert Pell quite some time now. So Robert, I think we can start with you, and maybe you can share your screen, and then yeah, floor is yours.
Perfect. Well, thank you so much for the introduction, Nabil. And it's a real pleasure to be here. And thanks for the introduction and invitation from EIT on this topic. It's a topic that's very close to my heart because it was the topic of my PhD, doing LCAs of rare earth elements. And I'm excited here to present a little bit about the work that we've done in that space, both the commercial projects as well as our internal research within Minviro. So I'm going to provide a few case studies as well and a little bit of practical guidance through some of our tools. But just to set the scene, if I can just go on to the next page, just to give you a bit of context about who Minviro is. I won't spend too much time on this. But yeah, I founded the company back in 2019, and we've really been focusing on conducting LCAs in the broad energy transition space, really supporting those companies with understanding the impacts of those raw material supply chains. We've done many LCAs across rare earths, and you're going to see a couple of the case studies today. We have an office in London, but we also have offices in China, in the Netherlands, and in Australia. We broadly offer consultancy services to deliver ISO compliant LCAs or compliant with particular regulation requirements. But we also have our software, which I'm going to give you a bit of an insight to today with our rare earth model in there to give it context. And we also provide data, and we've got very high quality proprietary data on many of the rare earth production routes that we see today, both primary and secondary. Just highlighting a bit of our capabilities, but really a bit of a shout out to EIT RawMaterials, who's supported us on our journey since day one. We've been involved in different research projects and grants, which have allowed us to get there today. But you can see some of our awards and some of the commercial projects that we work on as well. And I mentioned a little bit about the coverage that we have. Really, we started off upstream working with many material producers, mining companies like you can see there, like Alcoa and Rio Tinto, as well as rare earth producers and developers. But over time, that information is super valuable for the downstream customers that consume those materials. And that's very relevant for the topic today when we talk about permanent magnets and even when you go further into, say, motor manufacturers and then, that application in things like automotive. It's a really unique place for us to be because we get to see the aspects from different actors in the supply chain and the type of information that they need and the pressure that they're under to provide sustainability, product sustainability data, and product sustainability improvements over time. So I talked a little bit about services, but I think this really just is the last thing about Minviro, which then moves on to the regulations driving some of the requirements around LCA, PCF, or product sustainability in the rare earth space and the permanent magnet space. What we're seeing is that there's a huge sort of shift in the way that companies are prioritizing sustainability data, not just as a reporting exercise, but really to support with internal decision making at scale. And that's what we're seeing with some of the biggest enterprises today. So when we think about the sector that we're covering, when we're looking at rare earths and permanent magnets, I've kind of highlighted two very clear, distinct drivers that we see from regulatory pull of why we have to do this type of work today. Not just because it's super interesting and it was the topic of my PhD, but there's requirements for companies to align with upcoming or current regulations. And some of those direct influencing regulations can include ESPR, and many of you in the audience may have heard of digital product passports. They sound pretty exciting, and they are also a technical challenge, but it's really around understanding, the value chain of products and understanding the sustainability credentials of a product through the full life cycle and having that auditable and available for consumers or other stakeholders who might want to do that. And that's really in an exciting area under ESPR. There's obviously the Critical Raw Materials Act within the EU, and they've got some expectations around sustainability. So that's also a driving force, and we see quite a few rare earth projects in different stages of the maturity across the EU. And then there's some spillover from other regulations that might not be specifically targeted at permanent magnets or motors, but we're seeing the EU battery regulation, which we work a lot in that area. And then companies are often looking to scale what they're doing just for the battery space up over to other components, key components of electric vehicles or other applications. So we kind of see that effort being pulled over. We then have indirect drivers of this type of information, which might come from more from like corporate sustainability or due diligence requirements. And there's just been an omnibus release yesterday, so these are ever changing, and we'll see exactly where they end up. But you can see a couple of them here. I won't spend too much time on them, but some aspects which directly relate to sort of that supply chain and social indicator scoring, some which is around product sustainability and product carbon footprint, and some is around other hazardous waste materials that might be within supply chains or components. And this is just a very quick visual to highlight that we're seeing a status quo change in this space of LCA, where we're moving from static LCAs to a more dynamic ecosystem where there's mandated primary data in parts of the supply chain. And that's kind of what we do as a business. We really try and provide as much primary representative data at different nodes of the supply chain. And you'll see that as an example when we jump into the demo for one of the rare earth models that we have, which goes right from mine through to permanent magnet. I also wanted to give it a bit of a shout out to one of the EIT funded projects that we delivered with a few different partners. So we worked with traceability and digital product passport solution provider Circularize. And then we had industry partner Grundfos and BEC, so a permanent magnet manufacturer, also a European, very critical for this sector, and the Rare Earth Industry Association. And in practice, what we did, we created a product category rule, which is like a rule book and a framework for how you conduct consistent LCAs for the rare earth sector. And this really enables more of a like for like comparison, because often one of the criticisms of LCA is that if you don't have consistent rules and methodologies being applied, then it's very hard to compare one study with another. And this is particularly important for the rare earth sector because it is a little bit more challenging than other LCAs, because you often have so many co-products, and you're going to jump into that example of the multitude of co-products that you can have in a single system in the demo that we see. And then using that product category rules, we then created a integrated traceability and LCA solution, which was the whole outcome of that CIRES project. And you've got a bit of a visual here framework. But again, if anybody's interested in that, jumping into more detail on this, I'd be more than happy to spend hours talking about this topic because it's a really exciting project with some really exciting outcomes as well. So I'm going to jump into the part of the product that was used as that CIRES project with a case study of rare earth production. So I've got a little video that we have. So I'm not going to do too much on these features, but really what we try and create is, if you imagine, often the rare earth miner and the magnet manufacturer are very rarely the same company. And even if you go further down in the value chain, they're very rarely the same company. And so the ecosystem that we've tried to create is that you have a single system where multi-stakeholders can be involved, providing the data that's needed at different nodes within that supply chain. Great. So I have a video here, so I'm hoping that I can pull this out and just talk through as I go. So this is a rare earth project going from mine right through to permanent magnet. And you can see these are different unit processes that we have within this model. So you can see we've got solvent extraction and calcination, metal selection, and then the metal selection goes on to these different stages for magnet manufacturing. So all the different sintering, grinding and slicing, and electroplating. And what you're seeing on the right here is all those different co-products that you create within this system. So this single LCA model we can understand the impact of all the different products within that system that we're looking at. And we can make adjustments as needed if we wanted to make different processes in say, and I'll show you a bit of a demo of impact reduction. We've jumped into a particular unit process here, and now we're looking at the inventory items, so the materials and energy that's needed in this stage to produce the output of this stage. And you can see we've connected this to background data sets. In this instance, we've got EcoInvent that we're using. We're just showing an example of the underlying data there. So we're showing, okay, we're using sulfuric acid in this stage. And then we might want to see, okay, what are the drivers of that sulfuric acid impact? Is there opportunity for maybe swapping that out with another region of production? Now we're jumping onto visualizations of results. So what we can see is we can see the impacts of all the intermediate products, but I'm just going to jump into the example of the final permanent magnet. And we can see here the impact across all inputs, but we might want, and we can look across multiple impact categories, which is one of the true values of LCA, which is often underutilized. So for example, we're just looking between climate change and water-related impacts here as an example. We can also visualize results by contribution, and in this instance, we're looking at unit process stage. So we can see that in this permanent magnet manufacturing, the hotspots are in roasting and hydro and in electroplating. But that's for water impacts, but for climate change impacts, we can see that it's in the roasting and hydro and solvent extraction and calcination phases. So you can see how powerful an LCA model can be, not just to understand where the impacts are. You can also integrate things like life cycle costing, as well as many other data points that can help you with better decision making. And you can also visualize, say, the top contributors that might enable you to think about potentially how you could plan decarbonization or decisions within your system that you're studying. So now I'm just diving into a very quick case study, which is looking at an example of I want to run a decarbonization scenario. I want to see what can I do if I was, so I've just created another scenario. I'm now going to run a scenario. What about if I use a lower impact electricity input for all my stages? So you can see here very quickly looking across the whole system, and then I'm just going to run a scenario with in the same region. So this is in a region of China. I've just hidden some of the EcoInvent data to make sure that that's following their usage policy. But we can run a scenario where we are reducing the impact of the electricity grid max and seeing how that would impact the overall impact of the whole system or any of the other intermediate products. So really powerful. And you can see I'm just applying some bulk mapping features things here within Cycle, which allows you to do this in just a couple of moments. In my PhD days, it wasn't quite as efficient as this. It took me a lot longer. But as we've developed this, we've understood where the challenging workflows are. And now what's really cool is you can very quickly run a scenario comparison between those two things. So this is the last part of the demo, just to see sort of the results comparisons. So it shouldn't take too long to just go into the permanent magnet to sintered magnet here, or the sintering stage, and then we'll do a like-for-like comparison. So we can do the baseline comparison for that same material, the same products coming out of that system. And now we can see a comparison. And you can see with the lower impact electricity available in that region, so we haven't moved out of the region, we can achieve roughly like a 70% of the original value impact. And again, you'd want to apply LCA thinking. So you would apply that across multiple impact categories to make sure that you're making an informed and good choice. So for the next one, and I'm aware I'm going through quite quickly, so there's a lot of information here. So I do really encourage people to reach out if they're interested to dive into some more of these details. But we also recently had a public case study with Apple looking at permanent magnet recycling. for rare earth production and doing a comparison of primary metal production of the average, like industry average of that impact value. And what you can see here is the top level results comparison. So you can, we followed ISO standards and had a panel review, but you can see that recycling can reduce the climate change impact of NdPr metal production by 35% and dysprosium metal production by 25% compared to primary production. And then there's an opportunity applying decarbonisation scenarios, which I'll show you a little example in a moment, of reaching up to 65% and 60% of NdPr and dysprosium respectively. This is a little view around some of the project assumptions and the system boundary that we had for this particular model. And you can see that we have dismantled spent permanent magnets as an input, all the stages in that process with some final outputs coming in at the bottom there with some showing some key material inputs. What you can see here is some of the key hotspots and some of the like major contributors to the impact difference. That kind of creates a nice little visual there. But you can basically see that using recycled rare earth metals offers a 21% reduction in overall NdFeB magnet climate change impact versus primary routes. So that's the key factor there. And then this is the mitigation pathway. So showing that it's not just about stopping at the comparison, but looking at how you can further reduce those impacts. And what you can see here is you can see the lines that you're seeing at the bottom here, or sorry, the text that you're seeing here is the different scenarios that you can run for that decarbonisation scenario. And you can see the baseline starting point for this recycled NdPr metal. And then you can see this mitigated impact if we included scenarios such as lower impact hydrochloric acid or lower impact sodium hydroxide or maybe lower carbon electricity. And we can also see it here for the dysprosium metal as well. And again, just repeating some of the key takeaways. Now, this is a white paper that's publicly available, so you can dive into more details of this and see sort of more information around some of the underlying assumptions and some bit more contextual details around the study itself. So I think that's my time up. I appreciate that was going through extremely quickly, but yeah, thank you so much for the opportunity to present. And yeah, I don't know if we've got any time for questions, Nabil.
Yeah, thanks, Robert. Very excellent work and the background of building this database, and great. So maybe we have two questions, and perhaps we will take the main questions towards the end of the once finished. But maybe one questions now, and so is how does your software fare as compared to CIMA Pro or OpenLCA, and is it also ISO 14040 compliant?
Yeah, for sure. I mean, like I don't want to compare to competitors. Like, I mean, we see it. We've developed it to improve our workflows internally, and we think that there's an application. One, it's more accessible, logical, but also more scalable. So, like, we really see it's a cloud-based system, and it is compliant. I mean, we do a lot of work for example, ISO compliant studies on it. We've done hundreds of those, as well as EU regulation compliant, as well as some sector specific guidance, such as the PCR for the rare earth industry.
Yeah, thanks. The rest of the questions, we will take it towards the end.
Great.
And I also request the participants, if you have any questions, please put it in the question answer box. Then we will raise it in the end. Thanks, Robert, again. So I'll come back to you later. And as Robert mentioned, the EU-wide mandate. One mandate is that most of the Horizon projects have a mandate to have a work package on LCA and TCA, for example. And also that's also true for the EIT raw material project that we fund. We usually have the LCA related work package in these projects. So here we have 3 projects actually joining. One where we are partner and also sister projects. So the next one is from MAGELLAN, where EIT raw materials is also partner coordinated by the Orano, and we have Jan Klenner. And he is leading the work package on LCA for the MAGELLAN project. And Jan he has a PhD in industrial ecology from the Norwegian University of Science and Technology. And he joined, Lomatov. He represents Lomatov, who is a consortium member of the MAGELLAN, and he joined Lomatov in 2024 as a sustainability technologist. So he's done is a fantastic work for the Magellan and the Magellan, recycling routes and solutions based LCA based solutions. And I like to invite Jan for the presentation. Jan, floor is yours. Yeah.
Yeah, thank you, Nabil. And hello, everybody. I will try to bring up my screen.
Yes, coming.
Okay, perfect.
Yeah.
Okay, so thank you again for the opportunity to speak here today. I will talk about first LCA and LCC results for rare earth containing permanent magnets. And these are results from the MAGELLAN project. I will start with a brief introduction, also including a short overview of my company Lomatov, then some general notes on LCA and LCC, and then the role of LCA and LCC in the MAGELLAN project, some results for the baseline that we've been working on in the past, and also some thoughts on the potential for the MAGELLAN recycling route. So to start, I just want to introduce Lomatov. Lomatov is an environmental engineering SME. We are based in Valencia, Spain. We have more than 20 experts in sustainability, but also management and marketing, with more than 25 projects ongoing, both in private contracts and services, but also EU-funded projects such as the Magellan one. And we have many trusted partners at the entire European level. So we have two business lines. One is the Innova line that is focusing on providing technical support for companies and research centers to bring cutting-edge ideas to the market, targeting innovation policy and scale-up. So this may be regulatory framework analysis or support in standardizing processes. And then we also have the sustainable solutions line that is more targeting the assessment and optimization of resources, processes, and products to balance economic growth with environmental and social responsibility. And in this sustainable solutions line, we have the word sustainability, and we think about sustainability in three pillars. And this also covers the services that we have in this line. On the environmental side, we have methodologies such as eco-design or life cycle assessment. On the economic pillar, we have life cycle costing or techno-economic analysis as service in our portfolio. And then in the social dimension, we cover responsible research and innovation, but also social acceptance or social LCA studies. Then some notes on LCA more in general. So we work with the LCA framework on a daily basis, and you may know that this is a standardized framework to evaluate environmental burdens. So it's defined in the ISO standards 14040 and 14044. There are four phases to this assessment. There's goal and scope definition, an inventory phase, an impact assessment phase, and lastly, the interpretation phase. But those phases are not independent one of the other. So that's also what I try to visualize here with the arrows. They rather influence each other, and that leads to an often iterative approach. So an LCA is not always straightforward, but rather an iterative process. After the first round, we maybe come back to redefine goal and scope or collect additional information in the inventory stage. And in the end, what we try to provide with LCAs, now for the Magellan project as an example, is the identification of environmental improvement potentials or support research and development, maybe by providing eco-design guidance, but also, as we heard before, provide benchmarks or just reporting, support reporting compliant with a specific regulation. Now I have one slide here on each of those steps. So the goal and scope definition is usually where we set the frame of the study. And this is a good moment to introduce the words of cradle to gate and cradle to grave. So depending on what the question of the LCA or the question to be answered in the LCA is, we may want to choose one or the other focus. So if a question is rather the CO2 emitted to produce one bottle of water, then the LCA may cover all the steps that are included in the production of all the materials needed for production of water bottle, and also the manufacturing of the bottle itself or the production. But that's where the LCA would stop, so at the gate of the factory. Whereas if the question was framed rather as is bottled water environmentally worse than tap water, then an LCA would could also include the transport of the water bottles and the consumption at the end of life of bottled water. So what happens to the water bottle at the end? Is it recycled or is it just disposed and landfilled? When the scope is defined, then we often move on to the life cycle inventory phase. And this is in practice of the most resource consuming phase in an LCA because data is not always readily available. It needs to be collected. Data that, as we heard before, is collected for each unit process, so for each process in the value chain that is within the scope. And that is, in the end, it's a list of inputs, such as raw materials, but also other products from the human-made products, and a list of outputs, such as emissions, wastes, or products and co-products of the process. And then we move on to the life cycle impact assessment phase. And there are plenty of methods that are used to estimate the environmental impact of those inventories and of those product systems. What we tend to do is we stick to the methods recommended by the European Commission, also often mandated by regulations, and those are the environmental footprint methods, and they cover 16 categories, such as the climate change impact, which is often the most known one, but there are also ozone depletion, or other impact categories such as toxicity in terms of cancerous and non-cancerous human diseases. And then not really in the scope of LCA itself, but it often goes hand in hand. There's the life cycle costing. In the end, I try to say it's the same approach, but using a different metrics, a different perspective. So instead of looking at environmental questions, LCC, life cycle costing, looks at the environmental question, economic questions. Hence, the inventories also should include prices and costs, and the answers or the interpretations that can be given to those kind of assessments are cost drivers, savings potentials, etc. So how do we apply LCA and LCC in the MAGELLAN project? So as we heard before, MAGELLAN is a Horizon Europe project with more than 14 partners. It started in 2024. So we are now in month 26 of the project. And the idea is to have a prototype demonstration in an operational environment, and demonstration of what? So the challenge that MAGELLAN is addressing is that permanent magnets contain rare earth, as you may well know, and those play a key role in the green transition. But the value chains are often concentrated outside Europe, which creates a risk to supply for Europe. And especially in MAGELLAN, we look at the supply chains for electric vehicles, and there having a European supply chain would, of course, have create a benefit in terms of supply security. And then in addition, it is a fact, or it is known that nowadays permanent magnets are not really fully recycled in the European Union, at least. So in 2020, less than 1% of all magnets were recycled, and that could reach up to 400 tons of neodymium in 2030. So in other words, there's the potential to produce up to 800,000 electric vehicle traction motors using recycled rare earth and recycled permanent magnet material. And this is exactly what MAGELLAN is proposing. So there are a couple of innovations and circular economy business model ideas being proposed and being advanced in the MAGELLAN project. But maybe the key one is to use secondary rare earth materials in the production of new permanent magnets used for electric vehicles. In addition, in the use phase, the idea is to improve the motor design to improve permanent magnet recovery and potentially also reduce the permanent magnet mass per motor, and to facilitate further the recovery of permanent magnets and rare earth materials by upscaling the so-called magnet to alloy route. And this I have prepared on in the following slide, but first, also those ideas of circular economy and environmental benefits are also summarized in some key performance indicators in the MAGELLAN project. So the idea is to showcase how short loop recycling can reduce the carbon footprint of recycled materials and recycled magnets compared to virgin materials by at least 50%, and also have at least 10% carbon footprint reduction compared to long loop recycled materials. So this is a bit the overview of the MAGELLAN and the reference route. So the reference route is what is happening nowadays. It's more of a linear value chain where rare earth metals are produced from primary or virgin materials. They're then cast into ribbons, and those are converted into powders, which are used in sintering production of magnets. So I'm talking here about neodymium iron boron magnets. Then there are steps of component and motor integration and the use in electric vehicles, for example. But those three steps are not included in the life cycle assessment of the MAGELLAN baseline. So that's why they're in gray here. And then again, at the end of life, nowadays we assume that most permanent magnets in Europe are just downcycled, meaning they are not separated, but rather sold as ferrous scrap and maybe used in secondary steel production. So the MAGELLAN solution is really innovative here, as it provides an idea to how to recycle those magnets by collecting them at the end of life, extracting permanent magnets from EV motors, and then reusing them in the strip casting process after magnet to alloy, in an active magnet to alloy short loop recycling approach. What we have done so far in the MAGELLAN project then is to first create the benchmark, so identify the environmental impacts of the current value chain, the linear value chain, and this is based mostly on literature. We estimated with looking at all the available information that about 85% of current climate change impacts, so the CO2 equivalent emissions associated to permanent magnet production and use and end of life, are caused by the materials used, so by the iron and the rare earth materials, and just 15% are related to the actual manufacturing stage. So this is mostly the electricity or energy needed during the manufacturing of permanent magnets. There is quite some spread in the literature, so in available information. Every study identifies a different value. We dove a bit more into this and identified that there are a lot of different assumptions, for example, on how to treat different co-products, but also underlying primary data for rare earth materials. Those results and also the following ones are available in the forthcoming MAGELLAN report D5.3, which will be public. And then going a bit further into the impact of materials used for permanent magnet manufacturing. So we identified a standard or an average composition of permanent magnets used in EVs with a little less than 30% of rare earth elements and about 70% of other materials in terms of mass. But when looking at the climate change impacts, then the rare earth have a huge weight with more than 90% contribution in this impact category. And this is a picture that replicates also in other environmental footprint categories. So all the 16 categories recommended by the EU Commission. And for all categories, the materials, so especially rare earth, are the main driver for environmental impacts. In other words, by reducing the use of primary materials and substituting them with low impact recycled materials, there's a huge environmental gain possible. Then I also have a slide on something that's a bit of an addition to this study. So this is not, although I said the use stage is not the focus and not included in the actual LCA, we have some preliminary results, and they underline that the quality of recycled permanent magnets must be ensured so that the benefits gained during the manufacturing of them by using recycled materials are not lost during the use phase because of lower motor efficiencies. And then lastly, we also looked at the life cycle cost of the current permanent magnet production route. So what is an estimated cost for producing permanent magnets with current technology and current setting. And there we found a best estimate of 86 euros per kilogram of permanent magnet, assuming a production capacity of a factory of about 5,000 tons per year, which would require a capital investment of more than 300 million euros. And again, materials are the main contributor to cost and also the variation. So with looking at the 5-year high and low prices for materials, especially rare earth, we find that this 86 could easily become a value of 63 or 180 euros per kilogram, depending on the rare earth prices. So as last slide, I have the potential of the MAGELLAN solution. So this is something that we are still working on. So the project has not come to an end, and we are still working on the modeling of the actual MAGELLAN solution. But this is based on some information available in literature, at least partially. So we find that we look at the potential of the MAGELLAN solution both to reduce supply risk and the environmental impact of the PM production, and estimate that starting from the baseline value that we have established so far, and just by shifting to a cleaner energy mix, for example, by shifting production from China, which has a more coal-based energy mix, to a more European average with a larger share of nuclear and renewable resources, and by shifting the materials from purely primary materials to including also short loop recycled materials, it is well possible to reduce the climate change impact per kilogram of permanent magnet and to achieve this MAGELLAN KPI of an impact reduction of at least 50%. So this is something that we will try to demonstrate in the upcoming month with the LCA and LCC in the MAGELLAN project. And this is all I have for today, and thank you for your attention.
Thanks, Jan, for the excellent work that you are doing for the MAGELLAN project, and also, nicely touching on the LCC. That's a whole different aspects that that we could have another webinar, whole webinar for this, maybe sometimes in near future. Maybe one question before I move to the next speakers. In your slide, you mentioned about potential reuse of the permanent magnet. Do you remember that? And could you further elaborate on this? What is it?
I mean, there are different. I'm not exactly sure which slide you're referring to, but there are different strategies of how to deal with end of life magnets. So there are those 9R strategies, sometimes they're called, and in the MAGELLAN project we look at the recycling via the short loop. But there are, of course, also ideas to directly refurbish or reuse magnets without having to, without melting them or without you applying more complex chemical processes, for example, using long loop recycling routes. So there are those ideas of reusing magnets also directly. It depends a bit on the next application and what on the current, of course, also on the current status of the permanent magnets.
Yeah, we will take the questions towards the end. Jan, thanks again for joining. And for the audience, Robert has shared his link for his white paper. He mentioned that they published with the help of, or for the Apple, for the permanent magnet application in the iPhone. So you may have a look at that link. So the next one in the presentation is by Martin Coese. He's a PhD scholar at the Institute of Environmental Sciences at Leiden University. At the like Jan, he's also in the Department of Industrial Ecology, and he's representing a Horizon Project Resilience, where I think also looking at the short loop recycling of the permanent magnet, but also maybe a hybrid approach, mixing it with primary raw materials. So, Martin, floor is yours, so you can start your presentation.
Yes, thank you, Nabil, and thank you for the invitation to present. So my name is Maarten Koese, and as Nabil said, I'm a PhD candidate at Leiden University, currently almost finished with my PhD. And I worked on LCA of magnet recycling in the Resilience project. And I will present some results on this in the first half of the presentation. And then Stellina will take over. She's also a PhD at Leiden University. She will present some of the results of the Greenie project. I guess some of you are already aware of the Resilience project. The goal of the project is to build a resilient and more sustainable supply chain for magnetic rare earth materials and products in Europe by upscaling emerging and existing recycling technologies. And the project started around 3.5 years ago, so it's in the final phase. And we work together with many partners, as you can see on the slide, some industrial partners, also some academic partners. And Leiden University is responsible for the sustainability assessment of the project. And on the next slide, I will go into the LCA. So I don't need to go into the general principles of LCA anymore because the previous speakers have already done so. So I can delve into the assessed routes from the Resilience project. So what we did in Resilience is we conducted an LCA on different circular strategies for magnets and compared the environmental impacts of these with the impacts from primary magnets. So first we looked at long loop hydrometallurgical recycling, in which end-of-life magnet scrap basically serves as a rare earth ore, and the rare earth elements are extracted from it. The second route is the short loop magnet-to-magnet recycling, in which the end-of-life magnet scrap is processed through hydrogen processing of magnet scrap, or HPMS. And this results in neodymium iron boron powder, which can be directly processed into new magnets. And we also modeled a reuse route, assuming wind turbine magnets that are reprocessed into smaller magnets and then reused. And this is more or less a hypothetical route, but we decided to model it anyway to explore the impacts of reuse and also align with circular economy goals. And finally, then we looked at LCA of the primary magnets to enable comparison with the different recycling routes. And on the following slide, you can see the product system of each route, but I will not go into detail now because of the limited time. So I will go into the technological specifications of the long loop and the short loop recycling. So the benefits of the long loop hydrometallurgical recycling is that it's relatively versatile. It can be used for a wide range of waste streams. Also, if the scrap is contaminated, for example, with glue or epoxy coating from the magnets. And also the output of this long loop process is rare earth metal, which can be used for many applications also beyond making new magnets. But the downside is that it requires substantial inputs of chemicals and water. While the short loop is a bit less flexible, but it does preserve the composition of the magnet alloy. And this means that it can be directly remanufactured into a new magnet with a similar composition. So it's therefore more resource efficient, and also the energy and chemical usage are a lot lower. But the downside is that it's not suitable for mixed or oxidized scrap. So the input material needs to be rather pure to enable short loop recycling. And the data we got for the long loop process based on a pilot process, which is currently being developed by Macongo Resources. And we extrapolated this pilot data to an industrial scale. For the short loop, we got the data from the University of Birmingham and Hypermech, who are currently setting up a recycling facilities within the context of the Resilience Project. And also the reuse route we modeled based on data from expert consultations on how it could look like in theory, and also some data from the SUSMEC Pro project on the pre-processing of wind turbine waste. And then finally, the data from the primary magnet LCA was done based on the baseline as conducted in the SUSMEC Pro and Greenie projects, largely relying on data also found in literature. Then the results. As you can see in the figure on the right, you can see the LCA results for all the impact categories for the different routes. And the results are scaled to 100% for the route with the highest impacts. And as you can see in the figure, it's almost always the primary magnets that have the highest impacts, while the reuse route is associated with the lowest impacts. And as you can also see from the figure, the short loop recycling is associated with lower environmental impacts than long loop recycling. And in general, recycling is associated with a lot less impacts than primary magnets. The only exception, as you can see in the figure, is the impact category for ionizing radiation. And this is higher for the long loop recycling because we assume the electricity mix contains a bit of nuclear energy, which leads to ionizing radiation impacts, while for the primary magnet, the energy mix we used is largely coal-based. So for the climate change impacts, we see that impacts from the primary route are around 62 kilograms CO2 equivalent, the long loop around 24 kilogram, short loop 12 kilogram, and reuse 2 kilogram. And I mainly point them out here to show the differences in impacts for the different routes. Then in the next slide, we see the contributions to the climate change impacts for the short loop. And here we see that the impacts for climate change are mainly related to the virgin neodymium addition. So what we assume in the baseline LCA is a 3% addition of virgin neodymium hydride to improve the quality of the final magnets. And this causes considerable climate change impacts. And then also we see that the electricity that is used contributes to the impacts, as well as the pre-processing of the magnet scrap. And then in the next slide, we see the contributions to climate change impacts from the long loop. And there we see a similar picture. It's mainly the electricity used that contributes to these impacts, and also the addition of the virgin neodymium hydride. And then also the electro refining is a contributing factor here. In the next slide, we show the results of a sensitivity analysis we conducted. So as I just said, the addition of virgin neodymium hydride has a large influence on the environmental impacts, especially for the short loop, because the total impacts are a bit lower. For the baseline, we assumed a 3% addition of virgin neodymium hydride, but it's not always necessary to add this virgin neodymium. In some cases, the required addition might be higher if the scrap quality is lower, for example, while in other situations, the addition could be lower or even non-existent. And that's why we conducted a sensitivity analysis on this to show how the impacts would change for these different scenarios. And then we see that if the addition is 5%, then the impacts are 15 to 35% higher compared to the base scenario and depending on the environmental impact category. While if the addition is 0%, then the impacts are 10 to 50% lower compared to the baseline scenario. So this shows that actually this changing this virgin neodymium addition can do a lot for the results. And yeah, some conclusions from our work is that, well, as became clear, the greatest benefit in the environmental impacts comes from preventing magnets from going to waste. So recycling is a lot better than using new magnets. And long loop recycling already reduces the impacts by 62% compared to primary magnets, while short loop can reduce the impacts to around 80% compared to a new magnet. But the main takeaway is that recycling is definitely better than new magnets. Even if it's long loop, it's still a lot better. And then we also found that reuse leads to the lowest environmental impacts. But yeah, as we already said, it's not likely to be implemented on large scale anytime soon. And also in general, there's a lot of challenges still around magnet recycling. So the first one is a lack of data on waste streams and also on the end-of-life magnets. So often the magnet composition is not really clear of the magnets in the waste streams. And also how magnets are embedded in the products is not always clear. And yeah, of course, the collection of end-of-life magnets is challenging as well. And even if this succeeds, if collection is done properly, then retrieval of the magnets from the products is also a big challenge because they're often embedded in the products with glue or with some adhesives that make it difficult to get the magnets out. And what we also found in the resilience project is that the waste streams with the larger magnets are most promising for magnet recycling, for example, wind turbines or electric vehicles. But the challenge is that they will only be a substantial part of magnet waste in the future, for example, in 10 to 20 years. So yeah, this is challenging for recycling on the short term. And to conclude, we believe that a focus on design is really crucial to enable future recycling, to enable getting the magnets out of the products and recycling them or reusing them again. So these were some results from the resilience project, and then I will give the floor to my colleague Stelina.
Yeah, thanks, Martin. And excellent results and findings from the project. So have you published these results that the general public can access this? But also on a general question on the climate change impact, for example, you saw different routes, primary, and compare that with primary route. And can we compare this with the generalized data or is specific to the resilience project?
Yeah, so your first question was on if these results can be accessed anywhere. So I published or I wrote these for a resilience deliverable, which is a sensitive deliverable because it contains a lot of confidential data from the partners. But I am currently in the process of publishing my results in an academic journal without the confidential part. So this is in progress. And your second question, the climate change impacts results. So we specifically looked at the recycling technologies as developed within the resilience project based on the data from the partners. So yeah, these are relatively context specific. So I cannot really say much about if the difference between the primary magnets would and other recycling routes would be similar. That's something I think should be studied further. Yeah.
Yeah, we'll take the other questions towards the end. Thanks again for joining.
Thanks.
Now I move to Mr. Lena Samuel. Like Martin mentioned, she's a colleague of Martin, also at the CML as a PhD scholar, working for the Greenie project. Greenie projects, unlike Magellan or Resilience, is not on recycling but improving the material efficiency, and kind of things coordinated by our colleagues from Joseph Stephan Institute. And so maybe she can present some results or what she's doing on the LCA for the Greenie project. Thanks, Talina, for joining, and floor is yours.
Thank you. So first of all, good afternoon, everyone. Today I'll present my work on LCA for neodymium iron boron magnets, and particularly the environmental benefits of reducing the dysprosium content of the magnets. So my work is part of the European project called Greenie, which aims to re-engineer the microstructure of neodymium iron boron magnets to make them more powerful while at the same time reducing rare earth content, particularly heavy rare earth. At Leiden University, my mission in the project is to ensure that the new prototypes are better for the environment and also feasible economically. So during my PhD, I chose to focus on dysprosium for high temperature applications such as the motors and the generators of wind turbines and electric vehicles. The magnets usually contain a small addition of dysprosium to prevent the thermal demagnetization. It also improved the coercitivity, which makes the magnets even more powerful. So dysprosium mostly comes from southern China and Myanmar, where iron clay deposits are mined via in situ leaching. So basically, the technique consists of digging a hole in a mountain, then inject ammonium sulfate-based solution directly into the ground. Then the solution dissolves the rare earth, which are then pumped back to the surface. So the thing is that in Myanmar, mining financed the war is unregulated and highly destructive. It pollutes the water and the ground, which impact local ecosystem, but also local communities which depend on it to eat and to drink. They also work in unsafe conditions and are reporting medical problems. Another concern is that even when the rare earth are mined in Myanmar, they are always processed in China. And this independence on China is really problematic in terms of supply risks for Europe. So in addition to the social, environmental, and geopolitical concerns of dysprosium, we know that the climate targets set are leading to a growing global demand for green technologies, which of course increases the demand in magnets and thus in dysprosium. So therefore, limiting dysprosium consumption is really a crucial solution. So to do so, different techniques are possible, like recycling, as Martin presented, but also material efficiency. There are a lot of papers and projects, including Greenie, which are investigating the technical feasibility of reducing the dysprosium content in magnets while keeping high magnetic performance. Here you can see an example of a paper about grain boundary diffusion. But what we found missing is studies that are dedicated to the sustainable benefits of reducing dysprosium by material efficiency, including environmental benefits. So now that I spent quite some time on the context, let's move on to the LCA. The functional unit is the production of 1 kilogram of sintered UH grade neodymium iron boron magnet. UH grade is currently the minimal grade used for electric vehicles. The LCA adopts a cradle-to-gate approach, which means that all the processes from the mining of the rare earth, so neodymium from Bayanabo mine in China and dysprosium from ion absorption clay deposit in Myanmar, to the final shaped magnets are considered. We assume 6 different hypothetical magnet composition with dysprosium content varying from 1 to 8%. And finally, we assume 2 recovery rate scenarios for in situ leaching, a high recovery one with 70% and a low recovery one with 40%. The recovery rate corresponds to the proportion of rare earth that are successfully dissolved into the leachate during in situ leaching. You'll see that these scenarios strongly influence the results because lower is the recovery, higher materials and energy are required. So what did we find? First of all, as expected, lowering dysprosium content reduces impact for all impact categories, even despite increased neodymium content. For example, reducing dysprosium content from 4 to 1% lowers freshwater ecotoxicity impact over here by 39 to 63%, depending on the recovery rate. Also, we found that environmental benefits are more significant in the low recovery scenario. So, for example, reducing dysprosium content from 4 to 3%, so only by 1%, lowers land use impact by only 5.1% in the high recovery scenario, but by 21% in the low scenario. Again, this is because low recovery means more mining and resources needed. So dysprosium reduction is even more crucial in this context. Next, we performed a contribution analysis to identify hotspots in the production of neodymium iron boron magnets. The first analysis quantifies the contribution of the main production stages, so the mining, the refining of the rare earth, the alloying, and the magnet shaping. For each impact category, the first bar corresponds to a magnet with 1% dysprosium, the second bar to a magnet with 4% dysprosium, and the third bar for a magnet with 8% dysprosium. If we only look at the first bars of each impact categories, so the ones for a magnet with only 1% dysprosium, the production of neodymium oxide, so in light green, is always the most significant contributor. For example, it contributes to 85% of ozone depletion and 82% of human toxicity, carcinogenic. But then what we also see is that the production of dysprosium oxide in dark green has a really disproportionate contribution to most impact categories compared to its content. For example, if we look at marinotrophication, it's just 1% of dysprosium contributes to 41% of the impact category. If the magnet contains 4% of dysprosium, the contribution rises up to 71%. So here, the important thing to remember from this analysis is that the main contributor to the environmental impact of neodymium iron boron magnets is the extraction and the refining of the rare earth they contain. Next, we perform 2 additional contribution analyses to identify the contribution of each foreground processes to climate change and to freshwater ecotoxicity. We focused on climate change as it is the most widely recognized and policy-relevant impact category, and on freshwater ecotoxicity to acknowledge the potential toxicological impact associated with dysprosium mining. So for climate change, we found that 1 kilogram of magnet emit between 55 and 96 kilogram of CO2 equivalent, depending on the composition of the magnet and the recovery rate of the ore. The main contributors to climate change are the solvent extraction of both the rare earth, which correspond to around 58% of total emission, and also the in-situ leaching, so the mining of the dysprosium. The emissions are mainly due to the use of chemical and heat production. Now, for freshwater ecotoxicity, we found that the impact category is strongly affected by dysprosium content. You can see that the results vary largely from 1,300 to 11,900. The main contributor for the magnets containing only 1% of dysprosium is the solvent extraction of the rare earth as well, so here and here. But as dysprosium content rises, the contribution of in-situ leaching grows substantially. So for a magnet containing 4% of dysprosium, it contributes to 59% of the total impact. And so we found that the emissions of chemicals into water during in-situ leaching directly impact the freshwater ecosystem of the mining regions, such as Myanmar and southern China. So to conclude, even though the dysprosium represents only a small fraction of the magnet, now usually between 1 and 4%, it has a disproportionate contribution to environmental impacts. Material efficiency allows us to reduce the dysprosium content while maintaining magnetic performance. And so from an environmental perspective, reducing dysprosium is therefore a crucial strategy. It limits resource depletion, reduces environmental impacts, mitigates local pollution and health risks, lowers geopolitical dependency, and ensures a sustainable energy transition. So that was all for me. Thank you. And if you have any questions, I would be happy to take them.
Thank you, Stelina. Again, another fantastic study with great results. And maybe before we move to all the speakers, maybe a specific questions to you. So you only looked at the impact of the in-situ leaching of the dysprosium in Myanmar, or also you counter on the processing, for example, the solvent extraction stage there. And there are also other routes, not only in-situ leaching, but some dysprosium coming from other sources.
Yeah. So there is two types of rare earth. There is light rare earth like neodymium that is mostly coming from China, like Bayanobo mine, from Australia and from the USA. Then there is this heavy rare earth, and those ones, they mostly come from southern China and from Myanmar. So the difference is that where they mine the light rare earth, the concentrations of heavy rare earth is really low. So then it's not really economically viable to do it. So that's why they do it in ion absorption clay deposits, which the concentration is higher, around 5-6% of heavy rare earth. And so those they are mostly in southern China and Myanmar.
Yeah, okay. Thank you for that. Then maybe I'll go through the questions, some important relevant ones from the audience. Maybe I start with Robert. Questions from one of our former colleagues and friend. Robert, where did you put the system boundaries to allocate the rare earth after separation, and why? Yeah, it's difficult. Yeah,
It's a good question, and it's a challenge that we always have. So depends on the. I mean, I assume you're talking about the first study that we had in the cycle software. If I recall that we would use oxides as use economic allocation. So we followed the guidelines that we had in the product category rules. So we would conduct economic allocation based on the relevant oxide basis of the individual rare earths. And the reason for that is because it's often hard to find market prices at every stage of production.
Yeah, and also in your data, because others have project-based data sources, where exactly your data comes from. Yeah, it's quite tough to get the data, we know. Yeah.
No, it's all good. It depends on the study. I mean, I actually responded in the chat to the Apple study. So sometimes we get data directly from partners or suppliers or engineering firms, but we also have the capabilities to do a lot of that process simulation work ourselves as well. So we often do that process simulation internally as well. So we either get primary data directly from either real facilities or pilot scale or engineering mass and energy balances, or we produce it ourselves.
Yeah. Maybe I'll come back to you later. Maybe to Jan, from the MAGELLAN, we are building a pilot line, also part of the MAGELLAN. What are the key obstacles, as a general question, hindering the broader adoption of magnet recycling? You want to comment on this? And also maybe a second question on elaborate on the quality of magnets with MAGELLAN route using the recycled materials, yeah, as performing magnet, comparing that with the primary routes. Yeah, because we specifically say we are targeting the electric motors for this kind of route. So maybe you can give a perspective on that. Yeah.
Yes, two very good questions. So key obstacles to recycling, I mean, there are many technical and complications to this, but I think one of the main obstacles that we see now in the MAGELLAN work is not only the technical aspects, but also the economics of recycling in permanent magnets. So it is not so easy to get a good high volume stream of permanent magnets that is extractable and recyclable in an economic way. So there's a lot of at the moment there are a lot of manual labor, etc., involved to extract those magnets, and this of course makes the business case very hard, which makes the establishment of a recycling value chain still difficult in Europe. And then about the magnet grade that is being targeted in Magellan. So we identified an N44EH magnet grade, so a high magnet quality as the reference magnet, and that is also what is being targeted with the recycled magnets. So the idea is really to achieve very similar magnetic performance also with magnets produced in the Magellan route using recycled materials. The idea is maybe not to use 100% recycled materials, but start off with a mix of primary and recycled materials to both have the environmental benefits, but also ensure the high magnetic performance needed for EVs.
Yeah, and I also see there's also a question on the, on the LCC. You said something around 85 in your calculation. Is it an EU price for the EH grade?
This is based on my global market prices for materials and then prices as they could be feasible for machinery and capital investment in Europe. But we know that there's also, this is very uncertain. So yet this could be a Europe price, but for now we've based the assessment more on the current value chain, so more on the Chinese value chain without including any state subsidies, etc. So the actual market price may differ from the cost that we have estimated in the life cycle costing.
Yeah, thanks for that. Maybe this is a question for all. Maybe Robert, you could take lead. Can we consider applying environmental LCC that's monetizing the environmental impact? If so, why? If not, why not? Yeah, I don't know who are. Yeah, maybe Robert.
I'd love to jump.
Yeah,
I'd love to jump into it. I think it's a really interesting question, and it's some work that we do internally. I think there's some great case studies. I think there's a public one from Philips that they've done some environmental LCC where they kind of apply an economic value to the different impact indicators, and then you can start to really make. I think integrating that with more conventional LCC it really brings LCA and sustainability decision making into the finance and accounting world, and I think it's really powerful if you can sort of. But I think the biggest challenge that exists when you bring in those aspects is there are some European guidance under the PEFCR around what would be a value, or sort of in some European documents around the value of different impact assessment methodologies. But ultimately, different companies see that differently. And my maybe negative view on that is when we start to look at regulations, I think there's been missed opportunities because there's a bit of a carbon tunnel vision. And you see that sort of like European battery regulations, which is just looking at carbon intensity or carbon footprint and not taking into the breadth of impact assessment methodologies. So yeah, we do a lot of work with that, and it is super valuable, but I suppose the broader enterprise acceptance and it being embedded in regulations hasn't happened.
Yeah. And any further comment from other speakers? Yeah. No.
Yeah, I can just second this. I think this is a very interesting and good approach. And I think it's always a question of what's the question of your LTC that you're trying to answer. So if we talk more about the business economic perspective, then it's very difficult to include those environmental costs, as there's quite some ambiguity about how to evaluate different impacts, going beyond climate change impacts, of course. So that's, I think, why the default is to not include those environmental costs in standard LCC.
Yeah, thanks for that comment. Maybe a related one to Martin. You did give a result on the comparison of the primary and the different routes. And have you done either you or in the resilience project an LCC on the LCC for the projects or in general? Yeah.
Yeah, for me, it's difficult to say anything substantial about the differences in costs. I really looked at the environmental impacts. Yeah, and what I do think, what I would like to add to the points just made by the other speakers is that I think it's also important to consider this a bit broader and to also think about what is the worth of having such a supply chain within Europe and not relying on third countries for these magnets. And I think if we have to accept some higher costs, then maybe it's worth it. That's not something for me to decide, but that's something I think we all need to consider as well. Yeah.
Yeah. So maybe moving away now from the LCC, maybe is from for the project participants. So how do you assume regeneration of the magnetic properties through either short loop or long loop recycling from waste streams? Did you follow these questions or yeah?
I do not really follow the question. I can say something about this. So I guess it has to do with the virgin addition of the neodymium hydride that we assumed in our model.
Yeah.
And we assume this because sometimes it depends on of course, on the inputs of the recycling, what the output of the material will be. So especially for the short loop, if the inputs have a certain composition, then the output of the magnet alloy will have a similar composition. And depending on the kind of alloy composition you need for the magnet you want to build, it can be necessary to add some virgin neodymium hydride to it. So that's why we assume this in our model. But as I also said in the presentation, sometimes it's not necessary. So yeah, this has quite a large influence on the environmental impacts. So I would say if you can avoid this, then do it.
Yeah. Okay. So maybe now I move to Stelina. So somebody is asking, did you compare, the LCA of in China, southern regions, Myanmar, and also Australia, the different ore routes?
No. So for neodymium, I only assume Bayanovo as it is the biggest mine. So most neodymium is coming from China, and in China, Bayanovo is the biggest mine. I do know that it's also a mine in Australia and the USA, and there is actually a study from a colleague of us. I don't know if it's published yet. She's working on a paper who's actually comparing those three routes. So it's something we are looking into at Leiden University, but I did not compare those. It was not the goal of the study. And then, as I said before, dysprosium then is mostly coming from those young clay deposits, so really southern China and Myanmar.
Yeah. And maybe also another question, is any of you compare the NdFeB magnet with other kind of, like some new type like samarium FEN, and or especially Robert, if you have any chance to look at those LCAs?
Yeah, we definitely have. We've done comparisons across a broad range of NdFeB, but also, as you mentioned, Siberian cobalt or some other novel sort of like iron-based magnets. I think the hardest thing is functional equivalency when you look at different magnet types, because there's very specific properties around any NdFeB permanent magnets, even within slightly different, like nuanced compositions, which have very specific performance characteristics for their applications. So for example, if you might have a lower impact per specific function or per mass, but then actually when you look at the performance or application, it's very difficult to make a like-for-like comparison. And so often in those instances, you want to think of more the application of where those magnets might exist and extend the system boundary and try and find a comparable function. But in the instance of some of those novel magnet chemistries, some of them are unlikely to replace sort of like, say, a high heat environment in an electric vehicle as a motor or something like that, because the performance doesn't quite fit that criteria. That's our experience anyway.
Yeah, thanks for that clarification. And also for the LCC, do you consider only internal costs? Or if so, did you get them in the interviews with partners or from a specific database? Maybe both for Robert and also for Jan.
Yeah, I mean, getting costing data is, I mean, it's challenging because it's also there's a huge just like I mean, it's kind of like data gathering for the environmental LCA and LCC is really challenging because you have to find there's some public databases. So, for example, if you're looking for, say, metal costs, you've got sort of organizations like Fast Markets or Shanghai Metals Markets, which might have public information on pricing, but they differ in themselves. And then you also have, but there are also commercial databases which would do that work itself. But it's often a lot of literature research from our experience.
Jan, you want to comment?
Yeah, I can comment now for the. I mean, more in general, of course we try to use if we do a study with one specific partner, we try to use their primary data. But now for the Magellan example, where we based our assessment mostly on available information, we followed what Robert just said. So we tried to use publicly available market prices and got quotations for machinery and this way built a bottom-up model to estimate the overall life cycle cost. But this is, as I said earlier in my presentation, the data collection is a really cumbersome and resource-consuming step in the LCA framework.
Yeah, also again on LCC, is anyone consider the IP cost, or would you have some info on their contribution to the overall cost?
No, we did not explicitly consider this. This is something. There are a couple of costs that are not included in the quotations or in the price costs that I showed before, and some types of overhead costs are for sure not included, and IP costs are not included in what I showed. And this is I think the common practice, but if anybody else would disagree, please speak out.
Yeah, yeah, this is interesting, on usually in the previous one, we don't get this much of questions, we only have few questions, and the topic is really interesting. And so, as a final thought, maybe Robert, you can start on the general LCA or the challenges, or some insight for the people who are performing LCA or the industry. They are looking for the LCA because there are mandates, like recycled content and the environmental impact. You want to give a final thought on the LCA, Robert? Then I will ask others. Yeah.
Yeah, I think you mentioned one of the challenges. So, I mean, it depends again on whether you're doing an LCA on, I think a lot of what we looked at today is some of it is around like engineering studies or late stage development. They can be very different from operational LCA. So if you're reporting for regulations from actual operations and supply chain data, the challenges can be very different. We see kind of the three biggest types of sort of like work that we're doing in LCA at the moment is one is like really deep supply chain collaboration, and like the companies like large electronics companies or vehicle companies, they want to get all their suppliers engaged on an ecosystem so they can have data exchanges back and forth to align with those regulatory needs. We have those other types of companies which are trying to maybe do slightly different things where enterprises might need to do portfolio scale LCAs. So they need to do product like LCAs for all their products, and they might have tens of thousands. And that's a different type of challenge. It's connecting into existing data ecosystems. And then the third one is like just at complexity, which is, we've done a deep dive, and I think people have seen the complexity of a deep dive just into a permanent magnet, which is a part of a component of a larger component of a larger ecosystem, which might be an electric vehicle, which then again might be in a larger, you can really sort of scale out those LCA studies. And so for that, you need to be able to streamline a lot of this work and try and make the processes as efficient as possible. So that's kind of like those sort of things that we're seeing in the LCA world at the moment.
Yeah, thanks, Robert. Jan, you want to give us some final thoughts?
Yeah, I think from my side I can add. So we often work in those research projects where LCA is applied in quite a different way to what is asked by or asked by us for commercial LCAs. And so LCA is a very versatile tool, but there are a lot of different use cases and different applications, and each of those applications also comes with their problems. And the application of LCA in the research world is always I think it's very meaningful, but we always face challenges, and greater data availability and better understanding of those methodologies is really a key point to get some value out of LCA also for research projects.
Yeah, and Martin.
Yeah, I agree with what Jan just said, and I would like to add, if you really consider environmental impacts more broadly, then I would like to emphasize the role of design in reducing them, because we can do lots of LCAs on recycling and on magnets, etc. But if we cannot access these magnets or get them out of the products, then recycling will not happen anyway. So really think about design. If people are watching this and they're working on design of products, please keep in mind the recycling of these magnets in the end.
Yeah, then finally from Stelina.
Yeah, I'm not sure what to add on that. Maybe just one thing is I would like to say is that LCA should be seen as a tool, but it's not like the actual environmental impact. There is a lot of data scarcity, so we're doing as we can. From what I've seen, one of the main problem in my study was the recovery rate of the ore. It has a real impact, real differences, but it's also really hard to assess. And even more when I'm working on something like informal mining and regulated mining, then the data gets really complicated to find. So it's something to be considered as a tool to compare and to assess.
Yeah, then yeah, we're exactly on time. So thank you all my speakers for joining, and good luck with your European projects and PhD, and also Robert for new projects with big companies, and also for the audience, thanks for joining. Fantastic group, fantastic questions, very exciting. So we look forward to seeing you on our next edition, which is scheduled for March 19th on a similar topic. We will announce it soon. So thank you all for joining again. Yeah, bye bye. Have a nice day.
Thank you.
Thank you.
Thank
Yeah.
you.
Yeah.
Yeah.